So based on that derivation, we can generalize this to m-step transition probabilities. We have discussed two-step transition probabilities, and to write m-step transition probabilities, we will do a very similar thing. First of all, let's write what this transition probability is. X of n plus m equals j, given x of n equals I. You start from I, and after m transitions, you end up in j. So in between, you might visit any other state in your M transitions. So what I'm going to do is I'm going to condition this, again, to use the law of total probability. I'm going to condition this on the value of the random process, or the value of the Markov chain, at time n plus r. And r here is between 0 and m. Well, maybe I should also have written 0 less than r, because I'm talking about something later than n. Okay, so write the same expression based on the law of total probability. Probability that x of n plus m equals j, given x of n plus r equals k. So I visited k at step n plus r, and I was at state I at time n, times the probability of the condition, which is itself also conditional here. Probability of x of n plus r equals k, given I started at I. Okay. Now again, since x of n is a Markov chain, when I know x n plus r, the information about x of n is irrelevant due to the Markov property. Now you see this one here is an m minus r step probability, and this one here is an r step transition probability. Okay, so if I define m step transition probability using this notation, I can write this as probability of making a transition from I to k in r steps times probability of making a transition from k to j, whatever that k is, in m minus r steps. So in total, I will have m steps, and my transition will be from I to j. Okay, but in between, I just conditioned it on every state I can visit. This is called Chapman-Kolmogorov equations, and this Kolmogorov is, well, it's the same Kolmogorov with the Kolmogorov axioms at the very beginning of this course. That's another famous Russian mathematician, and Sidney Chapman is, I think, either British or American, I forgot, statistician. So this is the famous Chapman-Kolmogorov equation, which we make use to derive m-step transition probabilities. And we would like to write this in a matrix form. So if we define this matrix, remember P by itself was the one-step transition probability matrix. So if you would like to write the m-step transition probability matrix, each component at row I, column J, will correspond to the m-step transition probability from I to J. Okay, so we have derived this as Chapman-Kolmogorov equation, and if you just plug in instead of R, if you write m minus 1, what you have is this. This is the sum for over all possible k values, transition probabilities from I to k in m minus 1 steps, and in the final step, you make a transition from k to j. Okay, well, in matrix notation, you can express this as this matrix product. This is the m-step transition probability matrix. This one is the m minus 1 step transition probability matrix. And in fact, this expression defines matrix multiplication, right? If you have, like, let's say you have this matrix A, whose components are A, I, J, and let's say you have another matrix B, let's say the components are, well, let me just use K in between, not J. Okay, A, K, I, K, and B, K, J. Obviously, assuming that they are compatible, that we can actually multiply them. the product, let's say that is matrix C, and how can you write the component ij of C? You just look at row I of this matrix and column J of this matrix, right? And all components will correspond to each other, and this will be equal to this sum over all k values running in this way in this matrix and running in this way in this one, that aik times bjk. So this is the elementary matrix multiplication. So here, when you have this, you can write this in matrix form. M step transition probability matrix equals M minus 1 step transition probability matrix times P, the one step transition probability matrix. You can even write this like P1. Okay. If you continue this procedure like this, you will see that the M step transition probability matrix, in fact, is equal to the mth power of one-step transition probability matrix. So in order to obtain two-step transition probability matrix, you square the one-step transition probability matrix P. To obtain three-step transition probabilities, you take the cube, etc. Okay? Now, based on this, we can derive the distribution meaning the probability of the Markov chain being in each of the states in a given time instant, okay, if you know the initial state distribution. If you know that the initial state will take any of the states with respect to this distribution. This we call pi 0, the initial state distribution. Okay? So essentially how we define this is given here. Probability that x of 0, the initial value, is I. Okay? So if you just want to write after one transition, what is the distribution of each state? What you have is pi 1 in state I. Well, this is equal to the probability that x of 1 equals I. You see, this is not a conditional probability. Okay? Now I can write this again using the law of total probability. I will condition this on the state at time 0. Okay, so probability of x of 1 equals I, given x of 0 was k times x of 0 was k. Now this I have defined here, and this, as you see, is just one-step transition probability. So here I will just write this initial probability, and this here is one-step transition probability. And again, in matrix form, this turns out to be this equation. Pi 1 equals pi 0 times p. So you have the initial distribution. If you multiply it once with one-step transition probability matrix, you get the distribution of the states, meaning the probability of the Markov chain being in each of the states after one transition. You can again repeat the procedures we have done before, and you can arrive at the transient distribution in time instant m, okay, as well. Again, similar to Chapman-Kolmogorov, you can write this as the distribution at r times m minus r step transition probability matrix. Or, well, since we know this is equal to p times p to the power m minus r, and this again can be recursively be expressed in terms of the initial state distribution, pi 0. Finally, you can express the distribution, the transient distribution at time m, based on the initial state distribution as pi 0 times p to the power m. So what this says is, if you start in this distribution, this is the initial state distribution, and make m transitions, you can find the transient distribution at time m.